This video is an Excel tutorial for using Excel to make a PXY or a TXY diagram. In the problem statement prompt, I'm asked to do both, PXY diagram for water and acetic acid at 110 degrees C, and a TXY diagram for water and acetic acid at 1.2 atmospheres. For both plots, I'm going to assume ideal behavior. Making a PXY or a TXY plot entails plotting the bubble point and the dew point curves for both situations. So from my OneNote notebook, I've taken the equations that I derived in class for my bubble point and my dew point constraints. Let's start with the PXY diagram, since that one's going to be a little bit easier since temperature is set. The first thing to do is to look up the Antoine's constants for water and acetic acid, which I've already done. In the table that I referenced, it uses millimeters of mercury for the pressure unit and degrees Celsius for the temperature unit, and it also uses the base 10 form. This information is absolutely critical when you're calculating vapor pressures, because if you don't know what these units are, it's going to give you an incorrect answer. So I'm going to assume that you have no knowledge of how to use Excel here. So apologies if you already know this, but it'll be a useful review if you already know this. If I want to calculate a formula, I can start an Excel formula by putting an equal sign. So the vapor pressure of water, P star for water, is equal to, Antoine's equation is 10 to the power of, so the Excel syntax uses a caret for an exponent, a little hat, 10 to the exponent of A minus B divided by T plus C. So T is 110 degrees Celsius plus C. And when I want to substitute a value that I already have in another cell, I can just click on the cell and it'll import that value for me. Now I need to close out the parentheses that is on the denominator, and I also have to close out the parentheses that is the exponent of the 10. So that gives me my vapor pressure of water in millimeters of mercury. I'm going to do the same thing for the vapor pressure of acetic acid. 10 to the power of A minus B divided by T plus C. Whoops, I made a mistake there. I did not put the parentheses in the right spot. So if you ever encounter something weird, always double check to make sure that your syntax is as you expected it to. 594 millimeters of mercury is a much more reasonable answer. So I already have my vapor pressures. The next thing I want to do is to solve the bubble point and the dew point constraints. If you look carefully at the bubble point equation, I still have two unknowns for my PXY diagram. So temperature is set, and therefore the vapor pressures are set, but I still have unknown P and an unknown XA. Remember that because I'm assuming ideal behavior, I'm going to cancel the activity coefficients. So those are going to be equal to 1, so they're going to drop out. So in order to solve for the P, I need to set a range of values for XA. And I also need to assign which chemical, water or acetic acid, is going to be my component A. The typical convention in separations is that the more volatile component is assigned as component A. So looking at my vapor pressures, vapor pressure of water is higher than that of acetic acid. So water is going to be more volatile, and therefore it's going to be my component A. So I'm going to make a column in Excel for the mole fraction in the liquid phase of water. And I'm going to set a range of x's. So I'm going to start at 0, and I'm just going to add 0.05 every time until I reach 1. So I'm going to do the entire range of x's from 0 to 1. So all compositions of water and acetic acid. Now that my x is set, I can now solve for P. So bubble P is an easy equation now to solve, and the formula is given by this equation. So equals, remember, gamma A is 1, so it equals XA times PA star. And now because I'm going to be solving this equation multiple times, I need to $ this value, because when you drag cells, the cell references get dragged as well. So you'll see this in a second. I'm going to hit the F4 key, and that is going to double $, and that's going to keep my cell reference constant. Plus 1 minus XA, so 1 minus cell A17, times the vapor pressure. And I'm going to double $ that one as well. Now that I've done the calculation for the first case, so by the way, I should also see that my bubble point pressure is equal to my vapor pressure of pure acetic acid. And that makes sense because when there is 0 water in the system, I must have 100% acetic acid. So this bubble point pressure should match the vapor pressure for pure acetic acid. I can copy this formula down. In other words, I don't have to solve this equation 20 times. I can simply double click on the bottom right-hand corner and it's going to copy my formula down. Now, if I click on any one of these at random and I click the formula bar, I'm going to see that the cells that it referenced, like I said, if there's no $sign, it is going to drag the cell reference with it. But if there is a $sign, it is going to keep it constant. And I have to $sign, I really only had to $sign the row number here. I didn't have to $sign the column, but it's good practice to just $sign both just in case. So for example, if I were to drag this one to the right now, it's going to give me nonsense, but the cell reference, like I said, is going to drag unless there is a $sign. And if I didn't $sign the column letter here, it would drag one to the right as well. So this is a column of my bubble point pressures, and this is going to give me my bubble point curve. So before I plot these, I'm going to plot this in a moment. I want to also plot or calculate what the dew point pressure is. So in order to do that, I need to do the similar thing where I'm going to set a range of y's. So I'm going to have a column for y water. I'm going to do the same thing where I just pick values from 0 to 1, and I'm going to add 0.5 every time. Also, if you double click the bottom right-hand corner, that's also a similar way to drop it all the way down. And that you need to have that next to a column of data as well so that it knows where to stop, is the double click. But if you don't have that, you can just drag all the way down. All right, calculating the dew point pressure now will require me to solve this equation for pressure. So because there's a pressure on both the left hand, on both terms on the right-hand side, I can factor out the P and then solve for P by dividing everything else over to the other side. So my dew point equation is going to be 1 divided by a big denominator. So I'm going to have YA divided by vapor pressure of A, and that gets $signed, plus, I only need one parenthesis there, plus 1 minus Y water divided by vapor pressure of acetic acid, double $sign. All right, make sure that my parentheses are good. Excel also does a cool thing where it color codes your parentheses for you so you can check ahead of time whether or not they're all closed. So for example, these parentheses are red and these on the outside are black. So everything's closed up. That should give me a good answer. Just like before, my dew point pressure of my pure component should equal my pure component vapor pressure. So double click that all the way down. Notice, however, that the bubble point and the dew point pressures are in general different, and that's okay. The only place where they should be the same is at the pure components, and at pure water, I have agreement with what my Antoine's equation says it should be. All right, so now I have bubble point and dew point pressures. The next step is to plot both of these curves on the same graph. So I can highlight what I want to plot. So I'll plot the bubble point curve first, and I'll click Insert, and I want to make a scatter plot with a smooth line. So typically, I talked a lot about this in my phase equilibrium class. Typically, whenever you're modeling data or whenever you're not taking actual experimental data points, you want to have a smooth line here. And that signals to the reader that what you're talking about is a model. Now, this bubble point is not very aesthetically pleasing. So before I fix this, I'm a real stickler for making Excel plots look nice. So I'll show you how to make it look nice in a moment. But first, we need to add the other data set. So I'm going to right-click anywhere on the plot in Excel, and I want to click Select Data. That's going to allow me to add a data series. So the first data series that I've plotted, I can give it a name if I want. I don't have to do this. But I can name it bubble point if I'd like. And I can add a data series, call it dew point. This will only show up if I have a legend, by the way. And for this, I'm not going to have a legend, or I don't need one. My X values are given by my Y's. My X, as in the X-axis values. Remember, the X-axis is the composition, and that's of the vapor phase or the liquid phase. And my Y-axis values are my dew point pressure. Okay. So that looks good. I have a phase envelope looking curve here. Now, in order to make the plot look better, there's a few things that I definitely have to fix. The first are the grid lines. So I don't know why the default in Excel is to do these sparse grid lines, but grid lines are very useful if you want to obtain information from your plot. So I'm going to keep the grid lines, but I want to add some more grid lines. So on the plot, I can click Chart Elements, and under Grid Lines, I'm going to click the arrow to put some minor grid lines on the plot as well. And now I have some more grid lines that I can use to actually read this plot a little bit easier. Second thing I want to fix is the scaling. So the x-axis is going from 0 to 1.2 now, but I know from experience it stops at 1. I can't have a composition of greater than 100%. So I'm going to right-click the axis and click Format Axis. It's going to bring up the Format Axis toolbar. And under, all the way on the right on Axis Options, I want to truncate this to stop at 1, because anything beyond 1 is just a non-physical value. All right, and I can also change the units if I want, so I could make it go every 0.1. That looks a little bit nicer, but if you go too far overboard, you can make it look too busy. So I think that looks fine. I'm going to keep that. I also want to change the bounds of my y-axis. So I'm going from 0 to 1200, and that's okay, but if this is too far zoomed out, it can make it hard to read. So again, in order to make this graph easier to read, I'm going to click Format Axis, and I'm going to start the bounds a little bit higher such that my data gets a little bit easier to read. So this is a pretty good range for my data. All right, the next couple things are going to be purely aesthetics. So I want to add a border. So, I'm clicking on the grid lines. Sometimes you have to click it just right. So plot area, I want to make a thick border. This again is just to make it look nice. Let's go 1.5 thickness. And my fonts on the axis are gray, so I want to make those black. I could also adjust the size too. It depends on where I'm going to publish this graph or where I'm going to put it. Maybe I need a bigger font size. The font size in Excel is by default pretty low, so you might want to bump this up to like 12 or something. And you just do that by right-clicking and clicking Font. Also, the default colors for the curve are very Gator festive colors, but there's no reason why they have to be so bright. A solid black line does the job just fine. And I'm also missing axis titles. I absolutely need axis titles for my plots. So this is going to be my pressure in millimeters of mercury. Notice that I need both what is on the axis and the units, right? So the numbers are useless if I don't have what unit it is. So if I just put pressure, I don't know if this is atmospheres, bar, whatever. My x-axis is composition of water. And composition is a dimensionless number, so I don't have to have any units for this one. All right, notice how much better it looks already. The last thing I want to do is add a chart title. So sometimes you may not need a chart title, but for this chart, I want PXY diagram for water and acetic acid at 110 degrees. To type the degree sign, you just hold Alt and then 0176. PXY diagram for water, acetic acid at 110 C, and make it black. And I finally have a completed PXY diagram. Next, I'm going to draw the TXY diagram. All right, so back to the beginning, I'm going to start by solving my bubble point constraint for temperature now instead of pressure. And the problem I'm going to run into is that I don't know what the vapor pressure is if I don't know what the temperature is. So the way to solve this, if you plug in what Antoine's equation is, you're going to notice that it's going to be a nonlinear equation. I can use guess and check to solve this, and Excel is actually very useful for this purpose. So in order to solve the temperature, I'm going to make an initial guess. So I'm going to make bubble T as a column, and I'm just going to make an initial guess, and I'm going to have a constraint that must be true. So this bubble point constraint must be true if my temperature is correct. So I need to make an initial guess. Like I said, I'm going to guess 110 degrees C because should be about that. 1.2 atmospheres is about 900 millimeters of mercury or so. And if I look at my PXY diagram, 900 millimeters of mercury is at equilibrium. So 110 degrees C is at least close. I'm going to copy this guess all the way down. Now, because my temperature is going to change as I change my composition, my vapor pressure is also going to change. So now, instead of just calculating a static value, I need a column for the vapor pressures of my two components. So P star for water is going to be 10 to the power of A. And I skipped ahead a bit just to shorten the video a little bit. I've already shown this calculation. The only difference you have to be aware of, instead of 110, I've put the cell reference to the temperature. So if I change what the temperature is, say I put 50 C, it's going to change the vapor pressures as well. So this is, again, why Excel is useful, because I can change the calculation just by changing numbers, and it makes it to where I can visually look quickly and see what's happening. So if I just want to play with this a little bit and experiment, I can try many different temperatures to see what the effect on vapor pressure is. All right, so now I want to make this bubble point constraint true by solving for T. And I noted that I can't solve for T algebraically because it's a nonlinear equation. I've got to 10 to the power of the Antoine's coefficients. So the procedure here is to guess a value of T and then check that this equation is true. The way to do this is with the goal-seek or solver function in Excel. So I'm going to make a column called bubble constraint, and I'm going to plug in this equation. And what I like to do is, whenever I'm making an equation in solver or goal-seek, I like to put everything over to one side and set it equal to 0. And then that way I always remember what it's supposed to be. All right, so I need to know what the pressure is. So I have 1.2 atmospheres. I need to do a unit calculation real quick. So equals 1.2 times 760 is the conversion between atmospheres and millimeters of mercury, 912. All right, so I'm going to, in this column, I'm going to put equals 912, because that is the pressure. And if I wanted to be real fancy, I'd put pressure in a cell, which I already have. I just referenced the cell, but I know that it's not going to change throughout the problem. So 912 minus X water times vapor pressure of water minus 1 minus X water times vapor pressure of acetic acid. Okay, and obviously this is not 0 because I didn't guess the right temperature. So one way to do it would be just to guess and check. So try different values of T until I get 0. So let's see. I'm not getting close quite yet. I'm around that value. So instead of doing this all day, one way that you could do it is by using goal-seek. And I introduced this because this is going to be very useful to you in your career as an engineer. It's under the Data tab, What If Analysis, and I hit goal-seek. And goal-seek is a very simple user interface window. It says set cell, and this is the cell that I want to goal-seek. I want to set the value of this formula to a value of 0. Remember, I put everything over to the one side by changing the value of the temperature. If I hit OK, it'll then iterate and solve for my temperature for me. So I was pretty far off with my initial guess. It's 124 degrees C. All right, so one option is to, I'm just going to double click this all the way down and copy the formula, making sure that all of my cell references are what I want them to be. So all my cell references are dragging along with it. One option is I could hit goal-seek and do this 20 times, but that would be extremely tedious. Another way that I can do it, I'm just going to show you one more time how to use goal-seek. So hit goal-seek. I want to set the cell in E18, that's the next one, to a value of 0 by changing the value of the cell of temperature. All right, and I notice that my bubble point temperature is slowly decreasing, which makes sense. So again, if I don't want to go through and goal-seek 20 times, I can use solver. So you may not have solver on your version of Excel. It's something that you have to add in. If you can't see where solver is, just Google how to put solver or how to add solver into your Microsoft Excel. It's very easy to do. Just every time I have to do it, I have to look it up. So I'm not sure exactly where it is. This is also in the Data tab. So over in Analyze, again, you might not see it if you haven't added it in. It's something you do have to add in. I click the Solver button. And the interface is a little bit more complicated now for Solver, but you can do multiple equations with it. So I'm going to set my objective just equal to one of the cells that I want to solve for. So even though I already solved for this one, I'm going to set this value to a value of 0 by changing variable cells, and I'm going to click the entire range of bubble point temperatures. And then all the other equations I'm going to add as constraints. So I can add as a cell reference. All of these cells also have to be equal to 0 as well. And I also have to uncheck this box that says make unconstrained variables non-negative. I'm not sure why that is the default option, but I don't want to make that true. And then I click solve. And after a couple of seconds, Excel has now solved for my bubble point temperatures for me. So this is now the bubble point curve. Next, I'm going to do the dew point curve. So first, I want to make a copy of this stuff, and that's going to reduce the amount of keystrokes that I have to make. I want to be careful to put formulas, not values. All right, so I'm just going to change the name of this column to Y water, and change the name of this column to dew temperature. I just noticed bubble tea. That was one of my favorite drinks when I was in college. I used to love stopping at the bubble tea place and getting a nice beverage before class. All right, and the benefit of copying this over is that I still maintain my formulas for my vapor pressures. But now I need a dew constraint column. So I need to solve this equation in a similar way. And I'm just going to bring everything over to the other side again. So my dew constraint is equal to 1 minus YA times P, which is 912 millimeters of mercury, divided by vapor pressure, minus 1 minus Y water times 912 divided by vapor pressure of acetic acid. All right, and luckily, so this is 0 because I know what my dew temperature is. And again, for the pure components, dew and bubble point temperatures have to be equal. I'm going to copy this all the way down, and now I've got disagreement, but that's because I have to just go through and resolve for my dew point temperatures. So once again, hit solver. And now my objective is going to be in cell K17. The variables I'm going to change are my dew point temperatures, and my constraints have to be the rest of the constraint equations. And I hit solve, give it a couple of seconds to run, and now I have dew point temperatures. Now, because I already made the graph, I'm going to show you a shortcut for once you make a graph, you don't have to go through and do all the formatting again. Just going to copy and paste this graph. Click on one of the lines, and it's going to show me the bottom. I'm just going to drag the data that it's taking. All right, so instead of these bubble P's, I want to make it plot these bubble T's. And same thing for this graph, this dew point curve. I'm going to click and drag to give me the Y's and the bubble point, or the dew point temperatures. Now you might say, well, where did my graph go? And that is because all my temperatures are of the order 100 to 130. So I just need to right click, format axis, and I'll start at 100. And I'll go to, 130 looks good. There we go. And the only other thing I have to do is change my heading. So I have a TXY diagram for water and acetic acid at 1.2 atmospheres or 912 millimeters of mercury, equivalent statements. As long as you're specific about what unit you have, it doesn't have to be atmospheres. My y-axis is temperature in degrees C. And I'm just going to change these colors to black, and I am complete. So hope you enjoyed this video. This will hopefully be useful to you as you continue learning more about how to use Microsoft Excel. This goal seek and solver function are very helpful in many other contexts of engineering, not just drawing TXY, PXY diagrams. So it's a tool that you can hopefully use when the situation calls for it in the future. Thanks for watching.